Our speaker today, Pallavi, is a professor of ocean biogeochemistry at the Open University. She has a MSc from India, a PhD from the University of Cambridge, and has held research positions in both the UK and the Netherlands, as well as sitting on various international committees and UK grant panels. Today, she's going to tell us all about her incredible research on how she utilises chemistry to analyse deep sea mud to reconstruct past ocean and climate events, with a particular focus on the understanding of the past monsoon rainfall changes in response to climatic drivers. So, without further ado, over to you.
Thank you very much, Lorna. Thank you. Okay. What does this? It works. Thank you very much. Thanks for the introduction, and thank you for the invitation to the HOI and whole Orkney Science Festival team to give me this opportunity to talk to you about some of the research that I have been involved in. And just so that you know, I mean, there are a lot of people who are involved in this research, so it's pretty injustice for me to be standing here and speaking in front of you. But I was the generator of the idea, so I was fascinated by finding out why monsoon changes with time, how it changes, what are the drivers, how it will change in the future. So a lot of premise for the work has dictated from my early days and my bringing in India. And that basically gives me the purpose to give back something where I come from. And that you can argue is a much more stronger sense of purpose that gets me out of the bed every morning to do something about it, at least drive the research that I wish to do. I would like to particularly thank my graduate students, like PhD students. Katrina, bulk of the work that I'll be showing today is part of her PhD, was part of her PhD. She's now moved on. She's in Norway, doing her own, being an on her right, being an independent researcher. So, and some of my colleagues, particularly Phil Holden, who is a numerical modeler, who I had to convince to do some of the modeling to understand monsoon in the past. But it was really right that he kind of agreed to do so, because otherwise we wouldn't have made the progress as much as we did. So here's just an outline of what I'm going to talk today, giving a broader context as to why we need to understand monsoon in general. Talk about what are the tools that we use to then reconstruct climate of the past, really. And that's where I will probably go in much more detail about the mud, chemistry, a little bit, plankton, some of the models you can see in front, and then give you monsoon as just a case study, couple of snippet of kind of research findings that we have done over the years. And then summarize it to say what else we are doing perhaps next. Okay. So I thought before I go on and on about monsoon, just to give you I'm sure most of you are aware of this recent finding about the altar stone from the Stonehenge down in the south of England and its connection all the way from here, really, to be honest. Okay. So the reason why I'm bringing this story here to all of you is because the approach that was used in this study is more or less similar to what I will be talking about in discovering how monsoon has behaved in the past. Like in this story, they used minerals within the stone, and those were like apatite, rutile, some tiny, tiny minerals. So we are really looking at very small scale things to discover big. And hopefully you will see that connection in my talk as well. I'll be using tiny plankton and chemistry of the plankton to look at the Earth's climate in the past. Okay. And this discovery, of course, the headline grabs the headline, right? But there's a lot that goes behind it. So there was a chemistry of the rock, dating of the minerals, uranium, lead, and all other chemical compositions were measured. And then whole breadth of study was done to match it with all the possible linkage of stones that are found in the British Isles, to be honest, right? And and then also not only just analyzing them, dating them, but using statistics to convince everyone that yes, indeed, this is the connection that we are making. But that is just the science. What it then takes it a little bit leap of faith or reconstruction or whatever you want to call it, is then to say, back in the days, our Neolithic people were highly organized. They had mechanisms, transport mechanisms to bring these 6 tons worth of stones all the way from more or less Orkney to south of England. Okay, so that tells about a lot about our early evolution and how we may have had much more sophisticated way of doing things than we actually think, because now we think we have got much better system, of course, right? So and that came from all the discoveries that have been done in about the prehistoric time, about how people from Orkney they were transporting like cattle, some other stones of their likings, all the way from Europe as well as parts of the British Isles. So, what I'm trying to say here is, of course, there is science behind discovering connections in different parts, but also it tells us a lot about our own evolution, our own way of thinking, how that has evolved over time, how sophisticated we were even back in then that time, around 3000, 4000 BC. So it's a lot about making the story, using the science to just think about how we have evolved through time. Okay, so this is the common bit. So, so just giving a bit of perspective as to why do we care about looking at the past climate. And the reason is, I'm sure most of us are aware that the planet is somewhat changing its environment. And then if you look at the recent IPCC, which is a climate change report, what you see is with changing temperature, you also have changes in precipitation. And these are mainly numerical model-based observations and projections. Now, numerical models mainly is based on some equations, based on physics and the connections. So the main connection between the two figures that you see here is as you rise the temperature or as the temperature increases, the air mass gets warmer and warmer air holds more moisture. And therefore, it isn't a surprise that in the warmer world, you will have more moisture. That's one thing about having more precipitation. But getting the pattern of precipitation right is not that easy. Okay. So, although precipitation may be a lot. So, what we were interested, so, okay, globally, this is what is going to happen, but how are the continental areas are going to change or how are they going to respond? Will we have more in certain parts compared to other? So, then that brings me to a bit about monsoon. Why is it monsoon that's important? So this is a risk assessment done for a lot of things that we are going to lose or have disruption about due to the changing climate. And I don't have to do a lot to convince you that the highest risk with modest likelihood is disruption of Indian monsoon. Of course, the other two about the ice sheets, Greenland ice sheet loss, as well as the West Antarctic ice sheet loss, will have huge impact in terms of changes in sea level and therefore the coastal communities that depends or lives around the around the coastal area due to change of sea level that will have an impact. So, and the risk is mainly because of it's the population that the Indian monsoon actually depends on. Um, it is not unusual to see if you just did Google quickly about the monsoon, what is sorry, very intriguing. I did it on 3rd of September, 2 days just before I was flying. And every summer from May to July and August, you get this recurring. I mean, I couldn't capture all the way down, but you could see like from May it starts on and finishes around September. And the reason being the monsoon sets in early June. So May is very hot kind of weather. And then people start to think, oh my God, when are we going to get the rain really to get some respite from heat? But what it also does, while there's an anticipation for the monsoon to arrive, because agriculture, lots of things depend on in this part of the world what it also brings is massive disruption to life and livelihoods if it comes too much too quickly. Okay, and huge amounts of landslides, as well as infrastructure damage and crop failures too. Because I mean, I can tell you a story if you want to hear more. Um, where I come from, but when I was growing up, monsoon used to come very closer to my birthday in early June, and now it has already moved 2 weeks beyond. It now arrives more or less end of June. Okay. And because of that, all the farmers have to change their way when they are going to actually sow the seeds for the for rice paddy fields and things, or they are not aware of it, and then they end up with losing the crop because the monsoon comes later, and then either they die before they grow, or actually they damage because the monsoon rain comes much more later. At least in the recent years, they have found it to be almost prolonging in September and early October, which is much more damaging. Timing is much more damaging. Anyway, just to cut this story short, the basis is that we really, and the reason for these things is because, okay, yeah, we don't really know a lot. So this is the whole lot of projections, model projections for how monsoon is going to change in the future. Okay. And there are 32 models here that are being presented if you're looking at the regional scale. We are doing a slightly better than what we used to do in the previous set of models, which were 8 out of 20 used to agree to the sign of change. Now we have 16 out of 32, so now 50%. Yet 50% actually thinks that it might get drier. So there is, I don't know how many of you can buy something if I tell you there is a 50% chance of this working. I don't think many of you would, right? So that's where we are with this. And the reason that most of these models are based on what we look at the historical data, so satellite data, which is 50 to 60 years, and things that are changing at the pace it is changing is very different what it was in the last 60, 70 years. Okay. So that's where the past climate reconstructions are very useful, because on the shorter time scale, there are a lot of internal connections between the Earth system processes. Okay. When I say this, is like what's happening at the high latitude, i.e., changes in the ice sheets, might have has effect links to the changes in the cycle of the how the Pacific weather or the climate works. Also has connections with Amazon rainforest and with West African monsoon. But what I would like to draw your attention is a very limited evidence exists of the connection between the Atlantic circulation to the Indian monsoon. Not because of there isn't one, because we don't have enough evidence. We haven't got enough understanding of how things were in the past when the climate states were changing. Because believe it or not, we are in or moving into a territory that have not been seen in the Earth's recent past. Therefore, we need to gain much broader understanding so that those process-based understanding can bring into the models to be able to then predict it better for the future. Right. All this is huge amounts of things, big things. Yeah. But how do we do it really? You know, I'm going to now bring it back to you the way the altar stone story began, really looking at small things to then develop them first as a tool so that we as a broader, I'm speaking paleoclimatologists, can take it back in the time and then use it. So my training actually started during my PhD is about developing these tools. Back then, I had very limited knowledge about applying them, but I was much more focused in developing these tools. So, as a ocean um, scientist, chemist, basically, we want everything that we can get hold of. For reconstructing a complex system, you want multiple line of understanding to actually be very robust about how it is going to behave. So while we get deep sea mud, as simple as you can call that, we call it sediment just to make it more complicated. Um, we look at its physical look like, whether they are, how do they appear, what is the color. So here is, I've got two samples. I mean, you can have a closer look afterwards. One looks much darker than the other. I don't know if you can see, probably not, but believe me, it is. And the reason being, one is coming more from the closer to the continent, and one is much more in the open ocean. An open ocean one has more planktons, kind of dead planktons in it, so it looks much more whiter compared to the one that is near the coast, because near the coast you have got this huge river system bringing huge amounts of, clays, minerals, all sorts of things, broken down rocks, organic matter, all sorts of things, and they all tend to give darker color. Hence, the sediment color is the first we look at, like, ooh, that's changing. And there is always a reason why they fluctuate or change the color of the mud, is because that's what is in it. Okay. And then when we wash it, we can, if we look at greater than 63 micron, we look at all these shells. This is, by the way, from open ocean. That's why it's a huge amount of plankton in there. And if you look at the really tiny, tiny ones, it's the size is few micron, okay? So less than 63 micron. You've got a lot of these tiny, 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 tiny shell fragments. And while these are zooplankton, so these are animals, these are phytoplanktons, means these are plants of the ocean, but they make also cell. Okay, so they are useful in a way the same as the land plants, trees are, by doing photosynthesis, capturing carbon, making their soft tissues, but also they make the hard shell, mainly protection, perhaps from predation and other things. Still, they get eaten anyway. Um, so so we can use both. Yeah. So that also gives us a very rich amount of information locked within their shell, as well as organic compound that they have. And I'm just going to use an example in today's study, mostly this guy. And this is because they are very good at loving warm temperature, so staying in the top of the ocean, mainly in the mixed layer, so really surface signal. If you want to look at the sea surface temperature, these are pretty reliable things to measure. Okay, right. Of course, I described, so we are after all the ocean environment that we can get our um, hands on to, and then to get there, we look at species. So all of these bugs that live in the sediment, look at their species component. That they tell something is present is because they have preference towards something, right? If there is a more of a certain species present, you can even infer relative abundance of a particular species, can tell you about the nutrient condition in the surface ocean. So they are quite valuable. Okay. Or we can measure all the chemistry within them to then tell us about huge amount of ocean properties. And by using that information, then we reconstruct the past through time, how things have changed. One thing which I won't have time to talk about, but we also use shape and size of these shells to tell us about how changes in the ocean chemistry, particularly acidification in the ocean, is impacting these bugs to make their shell. They're really struggling and all the rest of it. But that's a completely separate project. Not today, but I'm happy to talk um, anytime later on. Okay, so when I was talking about my PhD, um, what you need for developing a tool is a very well constrained environment, because if you're going to link something with something, you need to know both parameters somehow, right? So if I'm going to find a temperature from the chemistry, I need to know the temperature. I need to have those bugs ready with me, plankton. And if I measure the chemistry, then I can find an empirical relationship, mathematical relationship between the two, so that then you can use that equation in the past, measure different things, and then say, okay, I can work out the temperature. So during my PhD, I didn't go, by the way, there, but because there was a when I was going to go, there was a storm, and that expedition was cancelled. But there is a very long time series of collecting plankton and recording data from hydrostation nearby. What it is telling me then, every time there is a sample collected here, there is also data available to them. And these are the data, basically temperature, salinity changes in the upper ocean, and you know the bugs where they live, and then you can work it out. Okay, and these plankton, the benefit of these plankton is that they are collected in this trap, literally a trap here. Okay, so this is funnel like this, and it sits above the seafloor, around 3,200 meter deep in the ocean. Okay, and they are being taken up every. So when I worked on first time series, it was every 2 months they were collected, but later the discovery happened that these bugs actually live 2 to 3 weeks in their lifespan. So then the actual time series also decreased. So every 2 weeks, these traps started to get collected, so that we get even better control on the on how they live in the surface ocean. And this is a very long standing and still ongoing time series where it's everything that is being collected from the surface ocean, trickling down to the 3,200 meter is being collected, and temperature and salinity and all other parameters are being recorded. Huge asset to have for scientists, basically. So I use these materials to then collect plankton and then measure their chemistry, mainly magnesium to calcium ratio during my PhD, because these bugs are basically made up of calcium carbonate, and majority of the thing is calcium and carbonate, but there are some impurities. We call it impurities because they are not favored by this plankton, but they are there and because of certain reasons. So that reason were discovered early on as being dependent on temperature. So by measuring lots of different species, what it does, because they are not, you cannot grow them at an environment that's not their favored living condition, for example. So for that, you have to use different species to get like a much broader temperature range for the thing. You can actually do that because what people do sometimes grow them in a tub like a culture experiments where they grow them and keep the things parameters fixed, so they only change one thing at a time. By doing that, you actually make initial discovery of what chemistry is dependent on what environmental conditions. So that's really good for first step, knowing what is dependent on what. But if you're looking at back in time, you really want to get to a system where multiple things are changing and then see whether that holds true. Because if it doesn't, then taking it back in time is not going to be any good because they may not relate at all. Sorry. Hi. So I just wanted to show you as an example, basically what we do then, we measure a lot of things. So we measure oxygen isotope of these bugs, and then we measure magnesium calcium, so we get temperature, we get oxygen isotope of that carbonate, and by using very um, earlier discovery in paleoclimate, we can get oxygen isotope of seawater, and that is basically dependent linearly with the salinity of the ocean. So by measuring two things, we get two things out effectively. Okay, so I'm only talking about these two today because these are the two things that I have applied. But hopefully, I'm going to touch upon on the discovery that we made as we applied these two things. We also found something new in the new area. Because with any new things, there are always challenges, but also opportunities. Okay, so now I'm going to take these tools um, back in time to then reconstruct climate, and in this case, monsoon. But we also look at ocean circulation. There's a completely separate project that's ongoing. We look at all sorts of things in the past. Okay, so what is monsoon, particularly Indian or South Asian or Asian monsoon? Basically, it's a huge reversal, seasonal reversal of wind rainfall. As simple as that. And that is because of the thermal contrast between, a lot of people think, land and sea, but actually it's mainly driven by interhemispheric temperature change. Okay, so that's how it's connected with the planet. And as you see during the summer, if you take this is like a um, um, satellite data taken out from 1951 to 2000 and just analyzed to get this kind of like average signal. This is what you would expect. So during the summer, you have these huge winds that blow from the ocean to the continent because also of the physics, because the continents heat up faster than the ocean, and therefore the wind blows from the ocean to the land. And as it moves over the ocean, it captures all the moisture and that it dumps it on the continent. And of course, in that favor, there's a huge mountain belt here called Himalaya, so that helps in any moisture going beyond past it. So you have a desert area over there, obviously. Okay, so that is that. But if you went to winter, the seasonal thing changes because now your continents get cooler faster, and therefore the wind direction completely changes. And because the wind is moving from continent to the ocean, they are drier, so they do not have the moisture. And this is therefore so much of predictability of it, because people almost take it for granted. Of course it's going to come. Of course it's going to come on time, because this is such a well-known phenomena, weather phenomena at least, and it also pretty stable over time too. But of course, because the system is changing so rapidly, there are so many changes at the moment that our predictability is different. So how do we actually capture this monsoon? It's very good looking at the instrumental data and say, oh yeah, this is all fine. What's wrong with this? But how do we go back in time and then capture these signals? So as I was showing, you have in the Arabian Sea, you capture this wind. There are lots of different types of, looking at the species, looking at the chemical composition of the mud, various things you can do, and then it tells you how it changes through time, and you can reconstruct and you can work it out how the wind pattern must have been in there. Now, if you come on this side, when we are reconstructing rainfall, what you will see is majority of record actually comes from continent, and you will argue, yes, why not? It's the rain which happens on the land that matters, right? But there could be this could be telling you something about happening at that location. Hopefully, I'll come to that when I talk more. But there's a huge gap here where you see this monsoon rainfall being captured, continental rainfall being brought by the rivers into the basin, and there was no record, or there wasn't a sea record that could capture the whole continental rainfall or as a means of runoff. Also, a little caveat is these cave records, while they're fantastic in terms of resolution, there are some gaps because it's not always to grow the stalagmites all the way through. So there could be some gaps there, but they are a huge asset without a doubt. So in 2012, 13, there was a huge initiative came to actually drill through the Indo-Pacific region to better understand monsoon. And I was part of one of these expeditions to the Bay of Bengal, and this was 2 months long expedition. You were on the ship doing everything, eating everything, basically 12-hour shift. It was not fun, like fun in the sense of just a luxury cruise, but it was an expedition. So it was 12-hour shift, 1 hour handover on either side, handover, takeover, whatever, and therefore 14-hour working and then rest, eating, sleeping, or whatever you can fit in within that time frame. Every single day, no weekend, nothing. So for 2 months continuous, and that was just fantastic experience because you're living and breathing science in that 2 months. Yeah, and it was really cool. This was the whole crew. So it was made up of scientists, engineers, um, technicians, hugely important because they knew exactly what we were doing. We knew less than they knew, obviously. And once you do all that, then you collect kilometers and kilometers of sediment sometimes from various different locations. They all get stored in a curation facilities like this. It's all labeled very carefully. You request samples, or sometimes you go in the lab where it's curated so that you can get like a whole core data before it gets sampled or destroyed. Oh, by the way, there's always they split the round core in half. So half is archive and half is being only sampled. So every single core that has been collected always have archive half. Normally the idea is not to touch the archive half, only work on the working half. But if it comes to that, like now the overall program has come to an end, there will be a justification to perhaps go back and look at some of the archive materials. We'll see how that goes. But anyway, once you request your sample, then you wash it in the lab and then pick using microscope. Although you see, if you 3D print them, they look much bigger and nicer. Unfortunately, they are so tiny. They are like size of a sand grain, so you really can't see with your naked eye. So you really need something more sophisticated like binocular microscope to help you identify those different species and then do unfortunately oops, yeah, I was told that if I click too quickly I will go. So then we do chemistry in the lab and then analyze using the plasma source mass spectrometer for all the chemical composition. This is what happens in the lab. So every single data point you see, there's a lot more work that has gone in. Okay. Now, just to remind ourselves, we are so these two stars were our location in the Bay of Bengal, and there was no data available on that sort of resolution. And what it's doing, hopefully, in this inset, what you can see as well from satellite image, is as you progress through the monsoon, you have this freshwater plume coming out of the continent through this of bay, and then it just moves that way. And this is basically draining uh, Ganges, Brahmaputra, Meghna, a huge river system, one of the largest river systems in the world. And therefore, it brings fresh water, whole lot of like clays and all sorts of chemical material dissolved as well as particulates. So all forms comes in there. And this one is of Myanmar, which is your Salween and Irrawaddy. These are also huge rivers. I don't have a picture, but you can almost see like huge amount of flood water just coming through and entering into the ocean. So these are very unique places, very close to the continent, yet in the marine environment to capture what is being brought by the rivers, but also some things like plankton who are not freshwater, they live, at least these ones live in the marine condition, which then allows us to probe the chemistry to work out what the ocean chemistry is changing. So what we will be after in this case is changes in the salinity of the surface ocean that is in response to the huge amount of fresh water coming to these areas. Okay, that's just the background. And for this, what we are doing, although it's all in one, we are going back in time. And as I was saying, there was a huge group of people on the expedition. So what you do is you almost suggest what you're going to do and get sediments. You can't have everything, obviously. So we have to work collaboratively. So first part was taken by a different group, and we got the samples for this interval. And the reason for this was that there was not much data available for this. And hopefully I'll come back to that later, where you will see why there was such a data gap. And I've put here the factors that we know at least have been recorded at high latitudes. These are Earth's orbital parameters for the time window we are looking at. And this is our last integration, or the Holocene, which is the warm interval, the similar sort of time period when this altar stone is being moved to all the way to from Orkney to the south. Um, Kind of thing, just to give you perspective. But this was the previous warm interval. So while we are looking at monsoon changes during the last interglacial warm period, how that responded to the change, we will also be comparing just the warm interval, just this bit, to the warm interval of the Holocene, and seeing what were the differences between the two. Because if we go back to the beginning, and if the warmer planet is going to have simply just more rainfall, we would expect the warm interval of the last interglaciers, which were few degrees warmer than the Holocene, we would expect more rainfall in Indian um, areas. Let's see whether we find that later or not. Before we go there, we will look at just the transition. Climate transitions are equally useful point to understand. Is like what is going, how systems are connected or were connected in the past. Okay, so what we will do here, just look at this window first, expanding this a little bit, because I'm sure you can see something abnormal happening over here. So this is effectively is the salinity record as it is here. And this is the temperature kind of thing. So you can see a little spike there, and then that follows with the spike in the freshening or the monsoon. And this is just two sides, one in North Bay of Bengal, the first one, and this is the of the Myanmar that I was talking about. Okay. So I know it's very complex. So there's so much more. I can just use this figure and just keep on talking about so many things here. Anyhow, but the point being, the spike that I was alluding to earlier is this a spike. And what it was clear, just focusing on the monsoon for a moment, it was clear that this warming, yeah. But by the way, this is the cold interval. This is the start of the interglacial right here. Yeah, this is the peak. Okay, all the way down. So before we had this study, it was considered in the science, paleoclimate, is this transition from glacial to interglacial was very monotonous. Nothing happened, literally transit from one to another. And in fact, if you go back and look at this here, you would say the same, right? It's just abrupt change, nothing more happened. But it isn't until you go and look at it high resolution, really pulling out. This is sub-millennial, 250 years record or to 300, 400 years. Okay, I have to rush. Anyway, what we found is that Antarctica or the southern hemisphere warmed, started the warming process of the deglaciation. And then it propagated to the tropics, which reflected in the enhancing of the monsoon. We also found the warming in the Mediterranean Sea, and then that linked to also the North Atlantic, uh, all the way up here near the Arctic. The same happened for the even the full, but this didn't quite materialize. Warming came, but didn't quite happen to make the whole deglaciation happen. And the reason being, because North Atlantic was still cooler, you have these ice-rafted debris that were found there. So it was still cool. It wasn't quite ready for full deglaciation to happen. So what then we did, we ran some statistical treatment to see whether um, that when did it happen, or whether indeed the warming started in the south and propagated all the way. And what you see then for the full termination is indeed you have this prolonged warming starting in the southern hemisphere, earlier in the tropics, like monsoon area, and then it went all the way up to the northern hemisphere. And that was when the full deglaciation of the planet actually occurred. So I'm going to rush now. Anyway, I'm told off. So just now going on to the warm climate. So for this, what we did is like, yeah, fine. You can go to a spot, look at the changes in the past, all good and well and good. But then we need to do better. How can we make sure that we look at the global picture? So what we did then, we compiled all the records that were published for this particular time window previously. And oh, that was such a job. Huge amount for the same time window. Everyone's age model was different. Everyone's proxy was different. Everything was different. Okay. Yet we said no, but we have to come up with something very simple out of it. Is the drier to wetter conditions. What were those two conditions? So you can see the background map is the model, and these are simply emplaced different records that were available along with our new records too. I don't have too much time to go in there, but what we started seeing that some regions, we divided into 6 regions, some regions were much more, so black is the average proxy record and yellow is the average model record. And they were both done independently. So no, first we did the proxies and then we talked to modelers to bring their things together. What what I was saying earlier, we wanted to compare the two warm intervals. So Holocene versus the last interglacial. The I don't have time to go in the detail, but what I want to say is that we were expecting Indian subcontinent to be wetter. So you can see the model is the background and the proxy records, if it's red, then it agrees with the model. So red, 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 red. There are some places where they don't agree, which is kind of expected anyway, because there's so much variability within these types of nature of material, types of proxies used, types of tools used, very different. Okay, but this was a real surprise. And that all through this last interglacial, you see the drying of the Asia. This was not expected. This basically alluded us to the fact that there are other factors on the submillennial scale that affects the rainfall. And what another surprise here was that what we started seeing that actually more rainfall was on the ocean rather than on the continent. And this was much more worrying because if the locus of the monsoon changes, no one on the continent wants rainfall to happen on the ocean. Trust me, that they would like it on the continent. Yeah, huge amount of water shortage and also so. But a lot of interesting feature here too. You can see the Amazon, really having the more rainfall. So you can see that. Also, Green Sahara concept also came. Another interesting thing you would see as you move up to the peak of the interglacial is that this area got drier. And if you remember the hominid evolution of early humans, actually, the migration out of Africa happened during this warm interval. And this was because the area where they were initially started to dry out and it started north of Africa. So moving out of Africa or north of Africa, northern side of Africa happened during this. And so all the evidence is there. You see greening of Africa, Sahara, for example. Also, there are some cave records, lake system found in this area. So it wasn't just a fluke. There are evidence that suggested that yes, and these are just some of the scientific evidence that were present for the time window to suggest that there were lake system, there are cave records. You're not going to have cave in Arabia if you don't have rainfall, for example, because to form the cave records, you really need precipitation to happen on the continent to be able to form those cave records. And human migration was one of the clue, similar to what I was talking about, ultrastone, right? Coming all the way from Orcadian Basin here in the red sandstone, 750 kilometer. If I told you that, people moved or from early humans moved from south of Africa to the northern areas because of changes in rainfall, you may say, that's a bit too much. But trust me, that was one of the reasons. So anyway, I'm going to leave the summary, but what I'm trying to say here that we look for something, we find something new, and then now what we are doing is going back in time and looking for those warm periods where we have samples from that expedition and we can do more and try to better understand so that all the future modeling and predictions of the monsoon could be we can have a bit more certainty in finding them. And most importantly, what I'm interested in is to look for those connections between monsoon and other. So, for example, loss of ice sheets, changes in the ocean circulation in the Atlantic. It has to have some relationship because you are moving huge amount of heat and salt water right across the globe. That has to have some connections with the low latitude climate like monsoon. With that, I'm going to just leave you with this beautiful picture that I took it when I was on the ship. I still use it. It was just too good. And would like to thank everyone, including funders, which is NERC, UKRI, as well as the UK IODP expedition. So huge thank you. And thank you to you all.
So much, Pallavi. That was a fantastic presentation. You can feel the passion you have for your subject coming across the whole room there. So thank you so much for sharing that with us. Does anyone have any questions in the room? We can get the microphone over to you. Or as we said before, if you want to scan the QR codes or go to Slido, we can get the questions up here. I know I have one in here, but my thing's going to sleep. Any questions in the room? Can't see. Nope. Oh, well, we've got one here for you from Eric. He says, it looks like after previous monsoon warming events, there appears to be a rapid pronounced cooling. Is that anticipated to happen this time around?
You mean present day or is it for the past? Can I just say, after previous monsoon warming?
Would you like to elaborate, Eric? Kaelin,
Sorry,
microphone.
can't see. Yeah.
Yeah, it looked like on one of the graphs, right? There was a
Right.
rise
Uh-huh.
in, well, it was rainfall, but it was related to temperature and salinity, or reduction in salinity. But it was almost like, yeah,
Mm, yeah.
that one, bottom left, right? So there's a warming, or right. So if you go to the bottom left of the left graph,
This one?
no,
This
no,
one?
sorry, I was going to the age, the very left graph,
The black one.
the black one.
Oh,
Yes,
this one.
yeah,
Oh, okay.
right.
This is
There's a
this is the global climate. This is not monsoon, by the way.
Okay, that's
Yeah.
well. It looks like there was a right a
Yeah. So
significant
this.
warming, and then a really
y-
rapid
Yeah, so
drop.
this is the ice core record from the Antarctica.
Right.
So this is the delta T. That's the temperature is recorded in the ice, polar ice, and then ice core. And this almost becomes our gospel, really, because these are the iconic climate record. So if we were to ever record anything or compare with the high latitude climate, you have to either go to the Greenland ice core or the Antarctic ice core records as being iconic because they're relatively pristine, you see, that they're not like a taken from somewhere which might be contaminated. But one of the things that I forgot to say, actually, not on this one, now that you have talked about that, I definitely forgot to speak. Uh, Here. So what we also found, somebody mentioned methane, I think in the last talk probably, what we found that this is the methane record, right, somewhere here, right? What we saw that actually Indian monsoon is strengthening when it happened. You also see a global increase in the methane emission. And this, what we said in the paper, obviously, is that the wetlands, effectively monsoon produces huge amounts of water and the wetland area, but tropical wetland were very highly connected with the as a source of the methane in the global record, basically. You see it here, you see it during the full glacier season as well. As soon as you hit the strongest monsoon, you also see the very strong increase in the methane concentration, which is another greenhouse gas, by the way. So, at least on the glacial to interglacial or submillennial time scales, when you are changing these climatic parameters, you are changing the climate, but also you are changing these flux of greenhouse gases, and there's a huge lot of other work that needs to be done to look at those connections in the tropics and in high latitudes. So
Excellent. Thank you. Anyone else got any other questions? Yeah, one at the back.
Hello. I found your graphs rather difficult to understand until I realised that your time is travelling from right to left rather than from left to right. So the convention with us is time goes from left to right when you're drawing something. Why have you done it from right to left?
That's a very interesting question. Thank you so much. The, that's the really as a paleo. If you look at any paleoclimate kind of reconstruction, they always go from right to left. Now we are trying to reverse it, but old hearts, it doesn't go away that quickly. So we have got our hostage to our kind of practice, really. We always put the time back and then we are coming to the modern where we can just flick it. Yeah. It will take some time because if we change it for this, then for the science we have to then flick it back because that's how people have um, portrayed time with. As we are moving forward, we are moving towards the. But yeah, it's
So
easily.
it's just a convention which is
It's just
opposite to the convention that we use in the everyday world. That's what you're
I'm
saying.
sorry. Yeah,
Yeah.
that's
Okay,
what.
thanks.
Just people want to make life difficult for everyone, right? So that's what they have done to us. They've just asked us, or the people community, basically. That's how they plot it. They plot it back. We are coming to the more recent or forward. I don't know why, but that's how been the convention, to be honest.
You think it's partly because the kind of archaeological effect, you're starting on the surface with the youngest and you're
Yeah,
digging down to the
yeah, deeper.
oldest. So
Yeah,
it's
yeah.
just that maybe in terms of the way the data is actually collected, you have to start with the newest before you can get to the oldest. Maybe give you an excuse anyway.
No, not really. That's in fact, we have to do random sampling anyway. So we do have, of course, we have to reconstruct time, and I think all the relative time scale against which we do our correlation with, they're all that way done. So you have the set record in the computer model that's already set. Now somebody has to go and put painstakingly the whole thing back to front. Then all of ours will also go back to front. It's just, yeah. It has been said many times. Just so
Uh, just a question really on presumably you can look at trends, but these are going to be over long time periods. And how is it possible to predict what a monsoon will do, say, 5 years' time, 10 years' time? Or do you need more data and more powerful computers? Or
yeah.
thanks.
Yeah, so your question is more about the time scale. So just so that the audience is clear, a lot of different factors operate on a different time scales. So when we are looking at millennial scale changes, there are different, slightly bigger kind of processes that kind of influence the changes in the monsoon. But when we come to decadal time scale, as you are talking about 5 years, 10 years, that sort of thing, there are lots of other kind of signals. So what we are looking at is perhaps some kind of mean state across several decades, because it's 250 years resolution for our record. But we are not saying that this can be directly used to predict the future. But what it can do is the models which are predicting the future is to understand what are the other factors other than simply the thermodynamic effect that if you warm the temperature, then there will be more precipitation. It is not as linear. There are some non-linear processes that are operating on different Earth system components. So therefore, that understanding, process-based understanding, how things are linked, what is going on, has to come from the past.
Yeah, I think the question that was asked was very interesting to me, because you're saying that there's been potentially a 2-week change in the start of the monsoon
Mm.
since you were a child, and
Mm.
without being cheeky, that doesn't seem to be that long ago.
Oh, it was a while ago. Trust me.
But the
40
thing
years.
is, I could see from the point of growing crops and that one more week of change could be catastrophic, and
Yeah.
therefore we may be potentially very close to it being a catastrophic change.
It is actually. It's very sad because there are, and also communication of the potential, because every year Indian Meteorological kind of department produces the projection. Because the couple of things that I did not get time to talk about, there are lots of other variability within the Indian Ocean that also dictates the monsoon possibility. So if in the Indian Ocean, particularly here, okay, so if the the temperature of the Arabian Sea, so or the Indian Ocean as a whole, so Western Indian Ocean, so all this part, yeah, if there is warming in the Western Indian Ocean and Eastern Indian Ocean is relatively cooler, that has some impact on the transport of the moisture as well, or general moisture control as well. That is called IOD, Indian Ocean Dipole. So that's this dipole is just changing in the thermal history of the two parts of the ocean. That works on a decadal scale. So those projections on year to year is based on how the sea surface temperature in the different parts of the Indian Ocean is actually regulating. On the slightly bigger scale is also your ENSO or El Nino, El La Nina phases, where you have Pacific, one part of the Pacific being warmer and other being cooler. Because let's not forget, this is not a good. I just wanted to get the, oh yeah, even here. So there is a connection. Have I got this? There's a connection between Pacific, although very restricted connection to the Indian Ocean. But that tiny, because the Pacific is so warm, tiny temperature or the water leakage through the Indonesian through flow to the Indian Ocean can dictate the sea surface temperature of the Indian Ocean, and therefore what monsoon will happen on a shorter time scale. Because And so, or El Nino, La Nina phases changes every 2 to 3 to 4 years, right? So those fluctuation on a shorter time scale, going back to the earlier question, on a shorter time scale, there are much. So what I'm trying to get here is that there are much more complex system at operation here. There are factors that affecting over thousands of years, and then the factors that are working on hundreds of years. Then but they don't go away, they are superimposed, right? So you can imagine something is controlling. So orbital forcing, external forcing sets the scene, if you like, okay, drama. But then within, so for example, Harvey has thought about this Orkney Science Festival. Okay, that's a big picture. There's going to be science talking. But within that, every session is going to be slightly different. There'll be some about chemistry, some about biology, some about ocean, some about planet, I don't know, moon, everything. Okay, so those internal variability, but overarching theme is going to, we are going to learn something about science. So external forcing sets the scene for how climate will happen on this planet. Okay, how Earth rotates around the sun, how the tilt changes, how the wobble of the Earth itself changes. All those have impact on how much solar radiation we are going to get on this planet, and that will dictate broad scale climate on this planet. But there are other factors within the Earth system that we are changing, or things are changing, or can be changed, either through changes in ocean circulation or changes in lots of other things, parts of the ocean, that can then dictate short term changes that we are going to face on this planet. And that's what dictates what you are saying about the year to year variability, or over the time variability. But what I'm saying, that the satellite record or data that we have isn't long enough at the moment to know exactly what we might be heading towards, what it would be in the future. And therefore, it's so hard to predict what is it that's underlying long-term variability that is dictating. How do we know that the changes in the Greenland ice sheet will not have impact on the moisture? One thing I also forgot to say is, while the models predict that warmer the ocean, more moisture it will grab, the changes in the interhemispheric temperature gradient are going to decrease because everything is going to warm up. Okay, if you decrease the temperature gradient between the hemisphere, what it does is, the prediction also is that the winds are going to be slower, or will not be as fast as it is currently, so they will become sluggish. So imagine a situation where you have lots of moisture, but the winds are not able to transport it to the various places. Of course, it's not a surprise when we saw that during the last interglacial we had rainfall perhaps just not being transported to the continent, but actually happening in the ocean. It would fit in that sense. But of course, that's just like one indication. I'm not saying that indeed is going to happen, but that's the understanding that needs to happen. To bring it to the solution mode, what you are kind of, how do we adapt to it? Actually, I don't know how well known this is. This is recorded. I'm sure I can say this. Um, um, Indian government decided, how many, maybe 5, 6, 10 years ago, I can't remember. So what we can do actually is, there are certain area where there going to be more rainfall. We are going to link our rivers in a way that, or geoengineer new river pathways or something. So where there aren't enough rainfall, we are going to connect the rivers so that we can transport the excess water back inside the country. So basically, we are rechannel the whole river system within India, or somewhat, so that where there is more rainfall, that will get channelized to places where there is lesser rainfall. That is well and good, and that's good. And I sincerely hope that has been well thought through, because I tried to write to someone asking about this, and I did not get well, I get a response, thank you for your interest in our project, and that's about it. And that's not what I was after. I was thinking more about, have you thought about then, if you are bringing less material, less runoff to the northern Bay of Bengal, what it would do to the biological system within? Because let's not forget, the coastal community is heavily dependent on the fisheries in that area. So if you don't bring in the nutrients that is being brought by the rivers, dissolve on all the other form, then that will affect the phytoplankton growth in this basin, and that will have impact on the fisheries that heavily people depend on. We are going to look into this. We are thinking of running some models and see what it would do to the future of the area in terms of its in terms of fisheries and also biogeochemistry of the materials basically coming to the through the rivers. If you don't bring it, what will happen?
But just thank you for coming, and thank you so much, Pallavi, for
No,
getting us
thank
all so
you.
excited about
Thank you so much. Yeah. Yeah.